Hello, Vinash.
Good morning.
Morning.
How are you doing today?
Doing good. How about you?
I'm okay.
Mhm.
I have I think 2 questions on exam.
Okay.
Can I ask you after this class?
Can we do it after 2 o'clock?
Yes. I mean
Okay.
today or tomorrow?
Today.
Oh yeah, yeah, we can do that.
Okay. Yeah. So I've told others also to do it at 2 o'clock. So you might have to wait a little, but I don't think each one of them will take too much time. So at the most, few minutes of waiting. Okay.
Okay.
Maybe 5-10 minutes.
Okay.
Okay. So are the questions clear, or is it there's a
Uh,
confusion?
I don't think there is. I'm only worried about number 3.
Okay.
So the thing is, in class we said if p subscript mu times superscript mu is 0, that means those two are Lorentz perpendicular, right? And then if p sub mu is time-like, then that means s superscript mu is space-like. But I don't know. I just think
Yeah,
that's too.
let's talk about it at 2 o'clock. I think that
Okay.
might be better instead of
Okay.
confusing you. Okay, that's better.
Well, I'm sure someone else is gonna ask that question. So,
Okay.
for this determinant and inverse of Lorentz transformation matrix, can I just use the method that I learned in linear algebra?
What other method can I ask you?
It is. I mean, there's like 2 or 3 methods. One is by finding the edge joint, but finding a edge joint of 4 by 4 matrix is a nightmare. I can tell you that. And there's the other method called row operation method.
Yeah, they're all the same. Like technically, they are all the same. Yeah, use any method. Yes.
Okay.
Mm-hmm.
And number 2, did you want non-relativistic energy momentum relation?
Oh, hold on. So I think so. There is a waiting room here. What does that mean? Hello? Hello?
I can hear you fine.
You can hear others also?
No, they are still connecting.
Why is everyone not able to hear me? There's another person.
I can hear you.
Oh, yeah. Okay. So Angela can hear me. Moses? Can you
Yeah.
hear
And
me?
now,
Yeah.
and now,
Hello.
now there are 2 Moses.
Oh, really?
Yeah, that's
Oh, that's right. Yeah.
it's okay. We have
I'm
more
working from
attendance. Jordan, can you hear us?
Yes.
Okay. Cool.
Okay. Can you hear me?
Yes. Yeah. Very well.
Okay, cool.
Okay. Okay. I think put the mic on my belt. I think that should be better. I think that was what we discovered last time. How are things?
Going all right.
All right. Are you getting sick of staying at home, or you're getting used to getting at home?
Well, I'm
No,
at home
I
with my
don't.
family, so that's nice for me.
I mean, I've never liked home, so
You don't like it? Yeah. Yeah. Okay.
How's it going for you?
Well, I think I got used to this. First week was a little. I was scattered here and there. It was a change, even though it was pretty much the same, but still it was different. But I think
Yeah,
now I got used to this schedule.
that's good.
I try to go out every day a little bit
Oh yeah.
for a walk or so. So that
Oh
makes
yeah,
me.
nice.
Yeah. So
Yeah,
that's otherwise okay.
good.
Yeah.
Yeah, I went out for a run yesterday and I wore a mask for the first time going out because I guess that's kind of the recommendations these days.
Yeah. Me too.
It felt weird though.
Yeah. Exactly. I think I too wore a mask for the first time in my life yesterday, primarily because I was supposed to get something for an older person, and I
Mm-hmm.
didn't want. I wanted to make
Mm-hmm.
sure that because
Yeah,
of
yeah,
me
yeah,
something
for sure.
doesn't happen. So I took precautions. Otherwise,
Mm-hmm.
I myself don't feel like I need. Oh, we are losing people.
we lost Angela.
So Angela and who else dropped off? Oh, and Moses was the
My
next
sex,
person.
my doppelganger left.
Yeah.
Yeah,
Okay.
my internet is kind of flabby today, so it might go on
I
and
see.
off again.
Yeah. Okay. Let's see how it goes. Yesterday, I heard the internet at my place was not good, but it didn't affect me at all. But
No, it's
apparently,
no.
it was,
They're having problems with Zoom.
they're
The
what?
server itself.
Avinash?
They're having problem with the server, Zoom
Mm.
server.
Zoom server. I see. I see.
I heard even non-China calls are being routed through China in Zoom.
I couldn't understand you. Can you repeat that?
What I was saying is there's a lawsuit claiming that in June non-China calls are routed through China. That means Chinese Communist Party might see us.
Oh, yeah. Not much to hide, I guess. I don't have much to hide. So I feel in all this privacy, the best thing is to not have any privacy.
Live out in the open.
Just keep everything open and I don't know. I could never understand these things. Okay. So let's see. Oh, there was a homework due today. Which homework is this? Did we finish the contents for the homework? I'm losing track of my own homeworks because you guys are not. I can blame it on you guys because you guys are not.
You can blame it on
So,
us. That's fine.
Yeah.
Yeah, homework 8 was due
Yeah.
today, I believe.
yeah, I'm just looking at the homework. Hold on. Give me a second. No, I'm also losing track. Okay, I just want to
I
make
think
sure that.
today's homework is a Kepler problem.
Yeah, so we haven't finished that. So I think we can postpone that a little. So homework 8. Let's say It's postponed to April. I think today I should be able to finish this. Yeah, and the midterm too. I think we. Oh, but yeah, this one is next week, right? Yeah. April 13, Tuesday. We'll talk about it
13th
later.
is Monday.
Oh yeah, I keep making that mistake. Quoting. It's written on my paper and I'd never correct it. Okay. So we lost Jordan now. Oh, he's waiting for me to admit him.
Yeah, that.
Did you guys have to wait until I admitted you?
Yeah.
I had to wait.
You had to wait, yeah. That's a new feature they have started. I think, at least when I was setting my settings for Zoom, I had made sure that there is no need to wait. But maybe I should go back and change that somehow. Okay. Anything else? Any general questions?
So I just got kicked for some reason, and then
Yes, I noticed. And also, when you come back, apparently you have to wait in the waiting room. So there is some waiting room, at least in my screen, it says. So that's a little tricky because I may not see it while I'm teaching. So if you get off, do you guys see that someone is in the waiting room?
No.
No.
Oh, so I'll try to pay attention. So
We'll know
whenever
if someone's not here anymore, though.
yeah, if someone is not here, then try to let me know that, okay, someone is missing and we should look for him or her in the waiting room. So yeah, okay, that's a new feature. I'll try to change those things if possible. Okay. Okay, we were working on the Kepler problem, and so again, we have two masses separated by a distance. And we already argued that motion is in a plane. Motion is in a plane. And once it is in a plane, then you're left out with only two coordinates. And we chose the radial distance and the angular distance to be the two coordinates, the cylindrical polar coordinates. And the Lagrangian is r dot phi dot, that's equal to half mu. So yes, I should point out what's mu. 1 over mu is there two masses, over m1 plus 1 over m2, correct? And r that is pointed out here is equal to r2 minus r1, right? That's a magnitude of the vector. So it can be r1 minus r2 or r2 minus r1, the distance between the two masses. That's what comes in. And the kinetic energy, it has two terms. So it's mu r square, and there is mu r square phi dot square. And the potential energy is negative, but since Lagrangian is negative of the potential energy, so we have G m1 m2 over r. Correct. That was our Lagrangian. We use the idea that angular momentum is conserved, and the fact that we can go to the center of mass frame to get rid of some of the variables. And usually this is reasonably straightforward, but we've spent some time on this to get down into this form anyway. So often this is a starting point for the Kepler problem. We also wrote down the Euler-Lagrange equations. We have dl. We can do this once more, right? So this is dl by dr dot is equal to mu r dot. That's the radial radial canonical momentum, or this is the how do you say generalized momentum with respect to the coordinate r, and the force in the radial direction has two pieces now, because even the kinetic energy is r dependent. So it is mu r, is that correct? I'm doing, yes, I think I'm doing correct. So this is phi dot square minus g m1 m2 over r square. Correct. And you have a similar equation for the angular coordinates, which is mu r square phi dot. That's your angular momentum in the z direction. And since there is no torque acting on this particle, so that's or there is no angular dependence in the Lagrangian, so there is no torque pushing it in the phi direction. This immediately tells us that the angular momentum will be conserved. So our equations will be mu r double dot is equal to mu r phi dot square minus g m1 m2 over r square, and this one tells us that the time derivative of mu r square phi dot square is equal to 0. That means this must be a constant. So this implies that we can define what did I do? There is no square, right? So that's equal to LZ. That's what we did in the last class, right? That's a summary of where we are. The angular momentum in the direction perpendicular to the plane, that's conserved. That's LZ for us, and this is pretty much the radial equation. This is your acceleration on the radial direction, but this is the centripetal acceleration. You would write this as mv square over r and put it on the left hand side, right? Both are inertial forces in the sense that these are acceleration, right? Mass times acceleration is equal to force. That's the way to read that equation. Any questions at this stage? Okay, there is one thing we can immediately see, and that is that if angular momentum is conserved, it seems to tell me that d phi by dt, d phi by dt is equal to Lz over mu r square, or let me write it the other way, or over mu r square, which means that a change in angle is equal to Lz over mu r square times dt. So I have a change in angle. So what we're talking about here is that, so there is some point here, let's say this is a reference point, and that is another point. So this is your origin, and this is the point which is moving. And if I were to make an angle phi here, so this could be, since we know that this will be an elliptic motion, it's something like this, correct? And a change in that angle is related to the change in time multiplied by some constant, not necessarily constant. LZ is a constant, but R might change, but it's a square of that quantity. This implies that there is an interpretation in here that whatever is a change in time leads to a change in angle. That means to say that phi keeps on increasing. There is no way phi can decrease. Once it starts moving in a certain direction, it cannot come back. So the claim is that phi is monotonic. Okay. That also means to say that phi can be used to measure time. Like any function that is monotonic in time can also be used to measure time. We can ask the question that how do we define time itself, correct? Is it a linear function? Is it a non-linear function? To begin with, we have the parameter t, and often we talk about its dependence. As far as we have another function that is also monotonic, that's a very valid definition of time. There is nothing wrong in it, but it cannot go back and forth in directions, because that's the way we understand time. And it is not very uncommon, because when we talk in terms of years, we are pretty much using the angle phi to measure time. So when we our notation of using years is dependent on the motion of Earth around the sun. So phi, the monotonicity of angle phi is being used to measure time. So, and we will see that very quickly. We will use we will start with time and then replace it with angle phi. Any questions there? Okay.
So instead of having
momentum, yes.
Instead of having
Yes.
phi repeat after it completes a 2 pi, rotation, it just keeps going.
Yes, that's correct. But if we keep a track of that number of rotations, it is still monotonic.
Yeah.
Correct? Yes,
Yeah.
It is periodic, but it keeps, if I keep track of that periodicity, I can make it a monotonic function.
Okay.
Does that make sense? Yes, it is periodic.
Yeah.
That's correct. Yeah, but even that can be used to.
Yeah. Yeah. Okay. I just yeah.
With that caveat that it is periodic. Yeah, but that's not very hard to make it monotonic system. Yeah.
Sure.
Good point. Yeah. There's one more immediate thing, an interpretation of this, which is the statement of Kepler's second law. If you have any curve, so let me write it on the other board. Oh, this is the other remote. So since we don't know yet that this is going to be elliptic or for that matter, hyperbolic or a conic section. So if we have an arbitrary curve in 2 dimensions, so this is your arbitrary curve. And if you go from point A to point B, so that's your change in, you're going from this point to this point, let's say you're going along that direction. And we can talk about the area, right? Infinitesimal area that is swept by this point along the origin. So you're looking at the origin, or you stand at the origin and you say how much area is swept. So the area here will be, if this is R, then I have R times d phi here. Right? So we are approximating this to be a triangle. So in the infinitesimal sense, dA, so the change in area is equal to r times r d phi. So height of the triangle times the base of the triangle divided by 2. Great. So the velocity of this area will be, in a sense, rate of change of area with respect to time. That will be equal to r square, so 1 by 2 r square d phi by so delta t, right? So that's dt. Right? And if you were to compare this with the angular momentum that we wrote down, I have to multiply by a mu, I suppose, correct? So this is phi dot. So if I were to, how do you say this? So 2, so I multiply by mu, I suppose. So 2 times mu times dA by dt is equal to mu r square phi dot, which is LZ. Which means that conservation of angular momentum has this equivalent statement that the area swept, the rate at which the area is being swept is a constant. And if we presume that this is a elliptic motion, which we don't know still, that means to say that if you have if you are when you're farther from the sun, right, so if the area has to be the same, that means you have to go faster, right? Or when you're closer to the sun, you have to be going faster if you want to cover the same amount of area. Okay. In this context, actually, what comes to my mind is, by the way, what causes seasonal changes on Earth? Or if I were to just ask from here, is summer at that point, or does the summer happen when you're farther from the sun or when you're closer to the sun?
Farther from the sun.
Say that again?
Farther from the sun.
Any other answers?
Man, it looks
Trying to
like it
mislead.
should be.
I know.
I'm trying to mislead, by the way. I'm being.
Well,
You
it
need-
happens. It happens when the axis is tilted towards, when the, like for the northern hemisphere, summer happens when the northern hemisphere is pointed towards the sun.
Yeah, that's a correct answer. I was purposely misleading in the sense that it's always tempting to think that, oh, it is a distance between the sun and the earth that plays this role, but the right reason is the northern hemisphere and the southern hemisphere. It couldn't be, because when we have summer, the southern hemisphere has winter, right? It is opposite. So it couldn't be the distance between the earth and the sun that is playing the role. It is actually the tilt of the axis that comes into picture. So if not for the tilt of the axis, we won't have summer and winter, right? The distances do not play a role. So again, the answer is it's always tempting to think like that, but it is not. The elliptic elliptic orbit does not play a role in the seasonal changes on Earth. Okay, is that clear? Any questions on that? So yeah, Moses, you pointed that out, correct? Yeah. Okay. And another, yeah, we'll come back to that when we are really talking about the elliptic orbit. At this point, so we have two immediate conclusions from conservation of angular momentum. One is that the area swept is the rate at which the area is swept is exactly the same, and by area I mean the angular area swept by the orbit, or the distance between the sun and earth. That's the same. And the second is that angle can be used instead of time. Right? That's not usually common to state, but angle in this problem, in the Kepler problem, works very well for time, and we will use that in a few minutes. Yeah. Okay. So with that, let's go back to our two equations, and let's use, now that we have angular momentum is conserved, I can use phi dot to be replaced with LZ, so that I have only one equation. So I have mu r double dot, that's equal to mu times r times phi dot is nothing but LZ over mu r square. Replace that. Square and minus of G m1 m2 over r. And that's everything in R now. All the quantities in this is R dependent. So I can rewrite this. So this is mu R double dot, that's equal to, let me, so there is an R here, there's an R raised to 4 in the term on the right, the first term on the right hand side. So that's a 1 over R cubed, correct? Is that right? Yeah, 1 over R cubed. So LZ square over mu R cubed minus G m1 m2 over, oh, I missed an R square there. So this was R square. This R square. If we were to begin from this point for all purposes, one can think as if we are thinking in terms of R to be a variable, that's mass times acceleration, and these are two forces. Right? Even though there is only one force acting, which is a gm1 m2 over r square, there's also seems to be a force, but this is a 1 over r cubed force. Right? And most importantly, one is coming with a positive sign, the other is coming with a negative sign. This is the attractive force that the sun is pulling us, and this is a so-called pseudo force, repulsive force, which is the centrifugal force, if you want, and that is 1 over r cubed. So in this manner, you can look at it as a potential, right? This can be thought of as a potential. Can we? So can we write this as negative change in potential over r? Can we write such a potential? And this is not the gravitational potential, we'll call it the effective potential, right? So there's an effective potential in there. So derivative of what will give you this 1 over r cubed? So let's think of that. So this is minus d by dr, and it is clear that it is negative 1 over yeah, help me here. So it is so I think LZ square over 2 mu times 1 over r square, and this is minus G m1 m2 over r. Let me see. So negative, negative, that's positive, but then I again differentiate it, so that gives me a negative sign, that gives me the second term. Here there is a minus 2 when I differentiate, that cancels the 2, also cancels the negative sign, and that gives me the first sign. So that's the effective potential. So this is your U effective. So for all practical purposes, we can imagine that this motion is happening with a under this effective potential. Okay. And let's immediately, when you have a potential energy, let's plot it, correct? So let's plot this potential energy. So this is U, and that's your R. Okay. And this is your effective potential, U effective. The first term is 1 over R square, so that's a positive term. So that's your 1 over R square potential. The second one is 1 over R, so it's a negative 1 over R, and it dies slower than 1 over R square. So that's this way, right? So this is 1 over R square, and this is 1 over R, or negative 1 over R, right? And with scaled with some parameters. So the GM1, M2 matters, LZ square over 2 mu, these parameters do matter because that gives weightage to the two curves. But either one, if we choose one of them, certain parameters, this is what happens. At very far distances, it is R is going to dominate or R square is going to dominate. At very far distances, R square will get killed very quickly. So it is 1 over R that dominates. So on the right hand side, this wins, right? On the left hand side, for when R becomes very small compared to a scale, which we will bring out very quickly, compared to a scale when R is very small, this one dominates. So on this region, this one is what dominates, right? So somewhere there has to be a transition from one to the other. So that means to say that it is going to cross the zero energy, right? So effectively, this will become something like this. Okay, and that's your potential energy, and that's the stable point. So this point is a stable point. If the Earth was going in a circle, that's your distance, how far you will be from Sun, right? If Earth was going in a circle, but we don't know that yet. So this point is special. So how do you find that point? How will you find that minimum point there?
Derivative is equal to 0.
I think I cannot hear you very well, but probably you're saying derivative of the potential being equal to 0, correct? So let's quickly find that out, right? And that will become a scale for our energy, and there is a corresponding distance there that will become a scale for our distance. Oops, this is the wrong remote, and I need to file, right? So let's calculate derivative, right? So which is pretty much the force, right? When I take the derivative of this, I have to set that to 0. So LZ square mu R cube, like let me call this R naught. Do I call it R naught? Let me see. I think. Well, I don't have my notes. That's further. So when it is really 0, this has to be equal to 0. So that's equal to G M1 M2 over R naught square of R naught cube and R naught square. One of them cancels out, and what I have is R naught is equal to LZ square over mu times G M1 M2. Okay. If you were doing hydrogen atom, what is that radius called?
Bohr's radius.
Yeah, Bohr radius, right? That's correct, very correct. Instead of G M1 M2, you will have Z E square, right? So instead of so G M1 M2 in hydrogen atom becomes Z E square and 4 pi epsilon also, right? right? If you're doing in SI units, that's what. And at R naught, you can substitute back your U effective. So, so we'll also have a scale U naught will be U effective at R naught. So this sets a scale. So this will be U effective, or I'm defining this to be U of output. So this is U naught, and this is R naught, right? So that sets your scale, and we will. So if you have a potential of this kind, and if I were to drop the, if I, in my initial conditions, tell me that, oh, I start my motion from here, right? Then it will tend to go down, and it will come back, and this will oscillate. Right? Is that clear? What at least visually speaking, if I were to start the ball here, it will go up there and it will come back. And since energy conservation has to be true, if you start from this point, you cannot go beyond that point. But on the other hand, if you had sufficient energy, if your initial conditions allow you to have a lot of energy, you can start from here, and it comes all the way, and it can go all the way to infinity. So that tells you that this need not be bounded all the time. At certain points it is bounded, at some other points it need not be bounded. But all that requires the fact that energy is actually conserved here. Energy should be conserved, but we haven't seen that statement completely yet. To see that, so let's go back to the first equation that we have and rewrite that in a minute. So let's go back to our equations here. R double dot is equal to mu. No, so I can write this now in this form. LZ square over mu R cube minus G M1 M2 over R square. Correct? With me? Let me divide all through by, or is that what I want to do? No. Let me multiply all through by R dot. Okay. So I multiply all the terms with R dot. That has this feature that R dot times R double dot is the same as R dot times derivative of R dot. That's the same as half d by dt of half R dot square. So my left hand side here is time derivative of half mu R dot square, right? That's kinetic energy. Okay. The next term here is I have 1 over R cube, and then multiplied by R dot. Again, I can think of this as time derivative of 1 over R square, correct? So if I were to take a derivative of this, I get a 1 over R cube, but then I also need to cancel that 2. So I need to do minus 1 by 2, I suppose. This is minus 1 by 2 also. Okay, so this is d by dt of minus 1 by 2 mu LZ square and 1 over R square. And that is the same thing goes with 1 over R and plus, there's a minus, right? So this is minus 1 d by dt of G M1 M2 over R. When I do the R raised to minus 1, that becomes a plus, so I need a plus, right? Okay. Okay. Overall, what all this means is that there is a total derivative of 1 by 2 mu R dot square and plus 1 by 2 LZ square over mu 1 over R square and minus G M1 M2 over R. This whole thing is equal to 0. This is actually the kinetic energy. If you were to replace this again in terms of phi dot square, this is nothing but the kinetic energy. And that's your potential energy minus, right? So kinetic energy plus potential energy, but potential energy is negative. That's equal to 0. So you identify that this is actually the energy. And you can show that starting from the Lagrangian, that this is indeed the Hamiltonian. Remember that Hamiltonian is what is conserved. So, but at this stage, let's not digress to do that. So,
Is
so
it
this
still
we will. Yes.
is
sorry.
it still LZ square in the second term?
Oh yes, LZ square. That's correct. Yes, LZ square. Right. Yeah, that shouldn't change. Yes, that's correct. Sorry about that. Right. Again, I think it's immediate. Since it's immediate, let's actually do one step there, since there is a question. So this is 1 by 2 mu R dot square. LZ was mu R square phi dot, right? So that is, so this is plus 1 by 2 mu R square phi dot square times mu R square minus G M1 M2 over R, that's equal to 0. Right. So d by dt of 1 by 2 mu R dot square. I have 1 by 2 mu, and then there is mu is what survives, and there is a R raised to 4 and R square. That's mu R square and phi dot square minus G M1 M2 over R. And that's, remember your Lagrangian, the term that comes in your Lagrangian, except, so is this a Lagrangian, by the way? What is off? Is this the Lagrangian? If you look into your notes and look at the first equation that we started with, is that the Lagrangian?
Looks like the Hamiltonian, isn't it?
Yeah,
Is
it is a Hamiltonian. This is off by a sign, right?
Yeah.
This is off by a sign, so it is not the Lagrangian. So let's try to see if you were to build the Hamiltonian. I think I have to change. Right. So Hamiltonian, remember, is P dotted with V, right? So P means the derivative of the Lagrangian with respect to R dot times R dot itself minus L. Right? P was mu times R dot. So this is mu times R dot times R dot minus the Lagrangian, which is 1 by 2 mu R dot square, and then plus
So why not just write it in terms of the Lagrangian instead of the Hamiltonian? So the Lagrangian is equal to PR dot minus H.
Tell that again. What's the question?
Why not just write it in terms of the Lagrangian instead of the Hamiltonian? And then you can just take the derivative
Because
of the
Hamiltonian
Lagrangian.
is the energy, right? So it is good to identify that this is conserved. Lagrangian is not conserved, remember.
Mm-hmm.
Like this time derivative of this whole quantity is 0. That what is inside is the Hamiltonian, right? Time derivative of the Lagrangian is not 0. Is that clear? Or maybe maybe I didn't address your question. So your question was, why not leave it as a Lagrangian instead of the Hamiltonian?
Yeah, because then when you integrate later, you can just replace the dl dt by minus dh dt.
Yeah, that's okay. That's okay. And in fact, I don't want to do this. This was just a digression. I'm satisfied with this. I just want this idea, right? That this is conserved.
Okay.
That is all I need.
Okay.
Okay. So this is just I was trying to trying to point out that this is actually the Hamiltonian.
Okay, gotcha.
Okay, that is also just an observation that this is the Hamiltonian. It's not like it might be trivial, but I'm stuck at this point actually. Is this the? That's not the Hamiltonian because I need to multiply the other coordinate also, right? Since there are 2 coordinates, so I need to do 2 things. So this is PR r dot plus P phi dot, right? So the momentum associated with R and the other quantity. So that's minus L, right? Then you get, so this is mu R dot plus this one was help. Let me look at here. So this is mu R square phi dot square. So mu R square phi dot square, and then minus of the Lagrangian, which is 1/2 mu R dot square plus 1/2 mu R square phi dot square minus G M1 M2 over R, right? So this pretty much switches the sign of this momentum because this is a sort of the trivial part in here. So that's indeed your 1/2 mu R dot square plus 1/2 mu R square phi dot square plus. What happened to my sign? Oh, this was plus actually. So this is minus. Okay. And here, instead of writing it as Hamiltonian, let me identify H as energy. Okay. So this will be your total energy which is conserved, right? It depends on your initial conditions. So whatever you begin with, once you have the energy set, that's going to remain the same all through the motion. That's what the idea is. So let's identify. So there is some constant. So this is 1/2. So what we have learned is that 1/2 mu R dot square plus LZ square over 2 mu 1 over R square, sort of repetition, is equal to E. Okay. And again, this could have come out in 2 steps, right, from where we started, but we sort of leisurely getting it in a sense. Any questions at this stage? Did I clarify that, Jordan? Why I was really doing it? It's not necessary, yes, but the first step itself gives me that this is a constant, but then I wanted to clarify that that's indeed the Hamiltonian. Like at this stage, you cannot say that is the energy, that is some constant. Agreed? We usually work with this parameter, we are so much used to it, we know that that is the energy, but if you were working on a arbitrary problem, it's not very obvious that that is to be interpreted as the energy. So only when it is a Hamiltonian, then you can say that that's actually the energy of the system. Okay, so there's a slight concreteness in there. Okay. Okay, so now let's proceed to do the differential equation. Okay. Till now, we are just playing around, writing things in different forms. So this, with this, now let's proceed and actually get the differential equation. So I'm going to rewrite that equation a little bit. So what I have is 1/2 mu r dot square. I'm going to write that as dr by dt square, right? And is equal to, let me put things on the right hand side. So I have E plus G m1 m2 over r, right? That's your potential energy that has gone to the right hand side. And then I have minus Lz square over 2 mu, and that's 1 over r square. Right away, let me divide out by mu. So this is the same as dr by dt square. Yeah, so this is squared is equal to 2 times E over mu plus 2 times G m1 m2 over mu times r, and minus 2, so the 2 cancels out. I have Lz square over mu square over r square. Right, so just took everything on the right hand side, take a square root on both sides. And what I gain is that this means that dt, so let me write it a little bit here. So dt, I'm leaving a little space on the left. So dt is equal to dr over one over r square. We are interested at this point in solving for the orbit or the curve in the plane that represents this motion. But at this point, we have a equation in r and t, right? So we will get r as a function of time, and we are pretty much ready to do this integral otherwise, right? Except for the fact that this is a function of time, we can do this integral immediately, like this is an integral, or at least it seems ready to at least attempt the integral. This is all r on the right hand side, t on the left hand side. But our motivation is to get the r as a function of angle, not as time. And that is where the time, the connection between time and phi comes in, angle phi comes in. We made the idea that time and angle, either of them can be used as time. So remember, d phi by dt, right, angular momentum conservation, tells you that Lz, what was it, mu r square, right? This was mu r square, correct? So I can replace dt with d phi. So this implies that dt is nothing but mu r square over Lz times d phi. Right. So that's a as good a parameter. They're monotonic, or one is connected with the other. So let's replace that. So this is equal to mu r square over LZ times d phi. And now I have an angle on the left hand side and r on the right hand side. So if I can solve for the radius vector as a function of angle, that pretty much gives me the curve of this orbit of this mass that is moving around. Okay, so that's a, like, first time when you do that, there is a understanding that goes in there. But as far as mathematics goes, that's just a substitution that you make in there with a valid substitution. Okay. After that substitution, it seems like r square, there is an extra r square that has come on the left. So take it on to the right again, correct? So we have angle d phi now equal to, so LZ over mu. So this is LZ over mu r square, correct? So LZ over mu r square, and dr over square root minus LZ square it seems like we can take, if I were to multiply this mu again, it's kind of undoing whatever we did earlier. We took a mu inside at this stage. Again, take the mu inside, that will kill that factor of mu in there. And I also want to do something, and that is, did I do this correct? What was angular momentum? Did I make the substitution correct? Oh, let me check this. Don't make an error at this stage. Yeah, this is okay. It seems perfectly fine. Okay, except that I want to multiply out by that mu in there, right? I can do that in the same step, but let me do that slowly. Okay. So that's equal to LZ, yeah, LZ over R squared. Right, so that's dr, and 1 over. So when I introduce the mu inside, I have 1 mu extra in the numerator, so in the first term, so that's 2 mu e. Same thing with the second term, I have mu times g m1 m2 over r, and finally this becomes LZ square over R square. Okay, with me? You want to integrate this. So when I integrate on the left hand side, I'll do, so this is d phi, and that's your dr, and we will have a constant that comes in. Let me call that constant the initial angle phi, right? So there's an integral constant, so that's phi minus phi naught. Right? This is not your initial, it can be interpreted as your initial angle, but at this stage, this is just a integration constant, phi minus phi naught. Whatever comes on the right hand side, I've brought it to the left hand square. And and to achieve the integral in here, let me substitute LZ over R as some S, right? So let me substitute. So let me write this here, right? Can I? Yeah. So what's LZ there's a space, LZ square over R square. I want to substitute as S. Okay. Or actually, I want to substitute LZ over R as S, so that its derivative will be 1 over R square then. So its derivative will be minus LZ over R square times dr is equal to ds. So if I make this substitution, LZ over R square becomes minus ds then. So I have minus ds, right? That's my first term in there. So that's a integral, and rest everything I simply have to replace R with S, R with LZ over S. So this is remains the same, 2 mu E plus 1 over R is S over LZ, right? So we have mu times G M1 M2 over LZ times S minus S squared. Okay, with me? Yeah, I think that's pretty much the substitution. And let me quickly. Okay, we have under the, oops, I have to change the board. And no questions, right? Okay, let me proceed. So 2 times mu times E plus mu times G M1 M2 over LZ times S minus S square, right? That's the quantity that is appearing inside the square root. I want to write this as a total derivative, right? Or a square quantity. So that's an S square. So there is a 2 here, there's a 2 there. So I'll do this as 2 times. So this is the same as equal to 2 mu E, and let's see, I have to make a minus and then a plus. So it's plus mu G M1 M2 over 2 times LZ square, and if you want minus of mu times G M1 M2 over 2 times LZ minus S whole square. Correct. So I added and subtracted an amount. So this is a small manipulation there, right? So there is a square of this quantity with a negative sign, square of this quantity, they cancel out. There is an S square that shows up, and the cross product has a factor of 2 times this quantity. So the factor of 2 cancels out, comes with a negative sign that makes it a plus. Right? So that's a good. Okay, is there a simplification here? I want to call this something, I suppose. Let me see. Yeah. So let's call this quantity C. Okay, let me call that quantity C square for that matter. So C square is equal to 2 times mu times E plus, and we'll come back and see what that is. that probably will have to wait till next time. So my integral becomes in terms of these quantities, and let's also, yeah, so this my integral becomes phi minus phi naught is equal to integral of, there was a minus, so there's a minus ds over c square minus of mu g m1 m2 over 2 lz minus s square and square root. It's immediate to see that you will substitute, what's the substitution you will make for such an integral? So 1 minus, it seems like it should be cosine theta, right? So, so let me make the substitution. Mu times g m1 m2 over 2 times lz minus s is equal to c times cosine of, let me call it, yeah, theta. Don't confuse this with any of the angles that's in the plane. This is not a dynamical parameter. This is just an integral substitution. Phi is your angle that's important. So minus ds is equal to minus c sine theta d theta. Okay, so let's. So we have phi minus phi naught is equal to minus ds becomes minus still. So this is minus c sine theta d theta over c comes out, and we have 1 minus cosine square theta. That's again a sine theta in the denominator, which tells you that this is simply minus theta. Okay, so that's your solution if you want. So phi minus phi naught is equal to, let's say, minus phi minus phi naught is equal to theta. Okay, but of course theta is some integral variable. You want to trace back your steps where what was your theta. That was cosine inverse of something. So c times, so what we have here is minus phi naught is equal to 1 over c times mu g m1 m2 over 2 lz minus s and cosine inverse of this, but I can put that on the other side, so that becomes cosine of that, right? So this is negative sign of cosine doesn't play an important role. Right. Any questions on the substitution? Very quickly, we will see interpretations of all these parameters. It will come up in the right place so that it will, each one of these will have a meaning as far as the orbit goes. Oh, it's 10:50, but let me quickly finish this. So S was Lz over R. So what we have is cosine of phi minus phi naught is equal to 1 over c times we have mu g m1 m2 over 2 lz minus s was lz over r.
Could you move the board?
Oh, I did not move it. Right. What does this represent? This is your solution actually. If you want R in terms of phi, so let me process this a little bit more. So this is, let me write this as minus, so we have LC over R. So C is that side, so LC over R is equal to, so LZ over R, bring it on the other side. Why is it so hard? So mu G M1 M2 over 2 times LZ, right? Minus, no, I didn't want to multiply that C, that was the point. So minus C times cosine phi. Okay. So R is equal to 1 over, so LZ, and the denominator, so it is mu times G M1 M2 over 2. Am I doing this correct? I'm flipping this, doing too many things at the same time. So it's LZ square minus C over LZ times cosine phi. So R as a function of angle phi is equal to so 1 minus C times 2 times LZ over mu times G M1 M2, and here we have 2 times LZ square over mu times G M1 M2 times cosine phi. We will define this to be R naught. Again, I need to move this. So this will be defined as R naught over 1 minus E times cosine phi. So whatever is the constant on the top, we will define that to be R naught, and it will come out to be pretty much the same number that we calculated earlier. That's a stable distance. In the earlier part of the class, we introduced that point scale in the distance R naught. And E is a new parameter that comes in front of the cosine phi, and that will be the eccentricity of this function. And this function, as of now, have you guys come across this function before?
Yes.
Yeah.
Like, yes?
We derived this equation using conic section, not using
Yes.
the potential in the Lagrangian. We used the idea of a directrix and other
That's
things
right.
in an ellipse.
Exactly. So this can be derived using the idea of a conic section in mathematics, and this is the solution to the differential equation that we got. And so you identify this to be a conic section, and which the interpretation of this, especially the eccentricity E that I didn't stress on too much today, and the R naught, and the actual paths that it can take. Why should there be so many different class of solutions, or the conic section solutions? We will talk about that next time. We are out of time today, but that's the solution you have here. So keep track of those constants. We'll come back next time and try to continue from this point on. And hopefully you've seen it, seen this in some form or the other. May not be in so detail. Even like I had to hurry a little in the end. I didn't go through the steps in as slowly as I would have liked to, but that's okay. Hopefully, that's the advantage of recording, I suppose, that you can actually go through this again if you want to. Okay.
We take phi naught to be 0, initial condition to be 0.
No, I did. Oh, no, I did not want to. Yes, you can immediately do that. I didn't mean to do that. Yes, so this is phi minus phi naught, actually. It's not necessary to really choose that. That's phi minus phi naught. Yeah. Yeah. But of course, yeah, initial condition is not really a significant issue there. Yeah. Yeah, I was not meaning to. Yeah.
Okay.
Yeah. Yeah, we had to do a few things. I had to do the Runge lens vector also, right? That also I want to emphasize. So yeah, I'm a little slow in this, and I have only we have 3.5 weeks remaining. Yeah, but we'll get there. And apparently it's a plus. Check the sign here. Could you guys check the sign for me next time? Yeah, check the sign. When I'm looking at my notes, it seems it is positive.
Is it because you define theta to be minus theta minus phi naught? And
Here,
then
here, right?
Because
Saying I
cosine
could have
minus.
substituted s minus that, and I could have been at the same place, correct?
mhm.
Yeah. So does that matter? Will anything else change there? So if this was minus, that will be plus, and this will remain the same. That would change sign. Yeah, probably. Yeah, that's correct. And then I would have got this was plus theta.
Plus theta.
Yeah.
Yeah, but that ends up
But
going inside of the cosine argument, and cosine is a
but then cosine is doesn't care for the sign, right?
right.
Think about it. I feel. Yeah, I don't want to change anything at this stage. Yeah. We'll come back to that next time. Yeah. I don't want to go through this again, though. Is there a problem here? Okay. Did I mess up? Okay. So if I were to do the opposite, yeah, but why not this? Like this is also a solution. Like my point is, why did I miss? Why did I not capture the sign? Or
Well, it's a good extra credit problem.
yeah, think about that. Maybe it is plus or minus is okay there. Is that the question is maybe if this was a plus sign, what's the difference? Is that allowed?
I've
Because
seen it
then
plus
R
minus.
would be, huh?
I've seen it plus minus.
Yeah, I think both are allowed here.
Depending on that closer or farther, it can be plus or minus.
Yeah. So the question is to figure out is both solutions allowed here or not? Just ask that question. Because in this case, it seems like as cosine goes from 0 to 1, so when cosine is 1, that's a maximum here. So it will go from 1 to 1 minus e. And in the other case, it will be 1 to 1 plus e. So yeah, think about what happens if that was a positive sign. So yeah, I had in my notes, I have it as positive. So
I think it can be plus minus. I'm pretty sure.
could be plus minus. Yeah, okay.
Like, what would it change? I don't think it would change anything. Because you end up taking, there's 2 square roots of a number, right?
Mm-hmm.
So that could be both negative or positive. And
Yep.
what would happen if you were to plot it? You would get
Yeah, because eccentricity, remember, goes only from 0 to infinity, the definition of the eccentricity. So it's not, oh yeah, the point is cosine function is positive and negative, right? Who cares, right?
yeah, because
So
if
yeah,
you
I think
plot, if
probably
you were to
that's what we mean.
plot, if you were to plot it plus
Yes,
or minus, you get the exact same graph.
yeah, you're right, you're right.
So,
I think that's the answer. Yeah, good.
So I'm looking at my calculus book, and it says it is plus or minus.
Yeah, it
Mhm.
has to be because yeah, if you plot
Yeah,
plus
I
or
can
minus,
change
it's
my
the
phi
same.
naught accordingly and get that. I can absorb this into the phi naught, that's fine. Is that clear? Like I can choose my phi naught in such a way that I can absorb that minus sign into it. Yes, so because and plot is the right way to say it. I think Jordan, you pointed that correct. If you were to plot it, instead of starting from 0, start from pi, and then you get the positive sign. Yes. So it doesn't matter, but we would like to write it as, so you will choose our phi naught in such a way that that's actually positive. Okay, good. So it's a good interpretation there. Yeah, why not negative? Yeah. Any other comments or questions? Sorry, I hurried a little there. And I probably will finish the Kepler problem. Maybe I'll take 3 more lectures. In one lecture, I'll go by going through all the elliptic orbits, parabolic, hyperbolic, and circular orbits. I think it's good to go through that, even though most of it is elementary. Once you reach here, it's just more of analysis of the solution. But I think it's a good idea to do that. And next one lecture, I want to do Runge lens vector, how that is conserved. There is a new conserved quantity, or there is a third conserved quantity. And then derive the precession of the perihelion of Mercury. That's a nice thing that comes out of this. So that's 3 lectures immediately. And then we will be left out with 2 weeks. And that's, so we will have only 2 weeks of relativity. So we might, which also I feel is important. So I'm struggling a little. So on Tuesday, yeah, so we are think about the exam also. So I'll talk about it on Thursday. How to, what we will do for the exam. Yeah. Okay, any questions or comments?
Not at this moment.
Okay.
I have one quick question.
Yes.
The book also says it could be 1 plus minus e sine of theta. Could it be? In
Yes,
this
again,
case?
phi, because phi naught, right? You can choose your phi naught whatever you want. So I think that's what I was trying to say. If I choose phi naught to be pi, so let's say if phi naught was equal to pi,
Yeah, then it would be plus.
right?
Yeah.
Then cosine of pi minus phi naught. So this is cosine of phi minus pi is
Minus cosine pi.
minus cosine pi, right? And if I were to choose phi naught is equal to pi by 2, then this is cosine of phi minus pi by 2. That's sine of phi. So you can write anything you want in principle there, and it's still the same plot, except that you changed your origin in a sense. So it's a matter of orientation of the ellipse. Is that clear?
Yes.
I think that clarifies that clearly. And
if you
geometrically, it has
choo-
to do with the point. Yes.
If you choose pi by 2, doesn't it just become a straight line? The function?
Why is it a straight line? Tell that again.
Because you have 1 by, 1 plus d cosine phi by, or pi by 2.
No, phi minus phi by 2, so it is sine phi, right? I don't change phi.
Oh,
I'm
okay.
choosing phi
Okay,
naught.
I got you.
I'm not, so because this was a constant, correct? Like that was a integral constant. So I can choose my initial conditions to be such that where I begin from, that's my point. So if I were to change my direction of the origin or whatever you call that orientation, then you can fix that. But we'll come back and attend to this. I'll clarify that pretty. I think I don't want to begin now because already I have crossed the time. Okay. I'll surely clarify these things so that there is no confusion. Okay.
Okay.
We'll begin from this solution and do everything. Reasonable, Jordan?
Mm-hmm.
Yeah. So, yeah. Angela, you there?
Yeah, I'm just listening to it.
Okay, yeah. You lost your video, yeah, usually.
Yeah,
Yeah,
I went up and then I came back again.
yeah, okay. Okay. How are other classes going for you guys?
Okay, I guess.
Yeah, not bad.
It sucks. This whole thing sucks.
Yeah, go ahead. Yeah, I don't know what to say.
There's nothing to say. It just sucks.
Yeah, you guys are unusually quiet today. So probably this is taking the toll on you guys.
Yeah.
I'm losing my voice.
You're losing, yeah, I could hear you now.
No, I'm losing my voice. Like my throat.
Why?
Oh.
You're losing your voice as you mean to say you're
I
getting
have
sick,
not.
is that what you're saying?
No, I have not talked to anybody in like two weeks.
Yeah.
Yeah, I don't even talk. So I'm just here silent.
So we should have more extended classes maybe. Give me 2 more classes and then maybe I can cover things better. But yeah, I don't think we should do that. Yeah. You guys must be having at least one of you, at least Jordan, I think has.
Yeah, I don't have time, unfortunately, but I would love that.
Yeah.
I just feel like it's hard to keep up right now, for sure. Just a lot of extra stuff that I'm trying to balance in my life.
Mhm.
Yeah.
So it's
Yeah,
okay
we
though.
will have a.
This is good practice for when the world's coming to an end,
No. I think you're taking it too far.
It's
I'm sure the world has seen this before.
yeah.
Hey,
How bad was
this,
what is it called, 1918 pandemic?
the
How bad was
Spanish
that?
flu? Apparently 50 million people died.
Spanish flu is really bad because I just learned this recently, but young people are typically safe from these type of viruses, but the Spanish flu attacked healthy people. So it
I
was the people that were sick and old typically didn't get it, but the younger people who had, because it attacked the immune system. So it was like if you had a strong immune system, your autoimmune response would make it worse. So young, healthy people were dying from the Spanish flu, as opposed to
Yeah.
the typical
I
unhealthy. So if you were born in 1918, you happen to be rich and fat and unhealthy, perhaps you had a better shot at survival. So the rich got richer and the poor got poorer.
I see. I see.
hey, it was not the worst. The worst was the plague.
Bubonic plague, yeah.
Yeah, that was the worst.
Which year was this?
1300s.
Yeah. That wiped away what, half of the population or more
Yeah,
than that?
1/3 of Europe.
Yeah, I think it was,
Yeah.
what was it?
It
I think
killed 1/3 of European population at that time.
I thought it was between 30 and like 70% of Europe's population. It was a lot.
Yeah. That's very huge. I don't remember what exactly it is, but it's a very huge in history that stands out, kind of big deal.
But for some reason, Italy seems to be most affected during these pandemics.
Who doesn't get affected?
It seems like Italy gets most affected during these pandemics.
Italy, I see.
Is there another one that you're referencing?
Yeah, bubonic plague, Spanish flu, all of them.
Yeah. I think a lot of people in, Southern Europe typically live together. So
There could be another reason for that. It could be like I heard Italy has a very large smoking population, so they already have breathing problems. So this corona thing, I heard it directly attacks your lungs, and if you already have a bad lung because of smoking, then you're good as dead.
yeah. Yeah.
Okay, so smokers get affected more, you see.
Yes, smokers, people who have diabetes, people who have cardiovascular diseases, they are the most prone groups of people.
Yeah.
Yeah, this says the bubonic plague may have reduced the world population from 475 million to 350 million.
So that's how much?
125 million.
Out of, yeah, that's almost 1/4, huh?
Yeah.
Why plague was worse is because right now this virus thing, it can, as of right now, it can only be transmitted from humans to humans. Well, if we don't look at the weight markets, yeah.
They said that a tiger caught
in Bronx, but
they
they have not recorded animal to human transmission if we don't look at the weight markets.
yeah, but apparently it's been transmitted from a human to a tiger.
Yeah.
So apparently they can catch it from us. So the potential of it coming back is also possible.
But plague was transmitted by rats, and rats are everywhere.
That's true. Yeah. There's no rats in my house. My wife wouldn't have it.
Neither.
My wife recently had a mouse that got into her car and made a nest inside of her air filter behind her.
Ooh.
Yeah.
Oh, wow.
Okay.
So it chewed a hole through the air filter, and the air filter is located like right behind the glove compartment in her car. So it was traveling in between the air filter and her car. So one day she's driving, and I think she was going to like the bank to, you know, put a check in or something. So she opened her box to grab a pen, and the mouse jumped out into her car. And she called me freaking out, of course. And so I found out where it was living and all of that, but it took like 2 weeks probably to get it to leave. There'd be a little mouse poop, you know, on her seats. And so she thought, okay, she hates mice, so she was gonna trap it. She bought like 15 of those sticky traps,
Yeah, yeah.
and she put them all throughout her car. And she's like, okay, I'm gonna give this thing, you know, a bunch of cheese, and it's gonna catch it. So she put like a giant stack of cheese on the trap. And the next morning she comes back, and all the cheese was missing, and no mouse. So the mouse, she had just fed this mouse this giant stack of cheese inside the car. So now it's definitely coming back. But yeah, it took a while. Yeah.
By the way, do you know the difference between a mouse and a rat?
The size? I don't know.
No, I heard a mouse has a gallbladder, but a rat does not have a gallbladder.
That's the difference?
Yeah, but if you look physically, mice are smaller than rats. Yeah, that is true, but
Rats
the real
are,
difference.
Genetically, though, they must be. Are they not distinct?
they are.
Yeah,
Yeah.
they are.
You know how they used to torture people? They'd take rats, and they'd take like a pot. So if they wanted to get some information out of you, but you weren't speaking, they'd bind your hands and your feet, and they'd take
And they let the rats bite you?
they'll take the pot, and they'll place the rats inside the pot and flip it over onto your stomach, and then fasten the pot down onto your stomach. And what the rats will do is they'll eat through anything. So they'll start scratching and biting through your stomach. That would be one heck of a torture. So they would eat through your stomach out your back to escape.
Wow.
I think I would probably talk.
Yeah.
It's worse than the methods that CIA uses, because hey, where's the glory? If I'm being interrogated like that, hey, I'll be interrogated, you know, with glory. A human torturing me, an animal, yeah, not gonna happen to me.
Yeah. They can just make up the excuse. Well, you know, we caught these rats, and then they were jumping around and just happened to push the pot off of the desktop onto the guy's stomach, and it wasn't our fault. Just happened. But he was bound. Well, I don't know. He's kind of weird like that. Okay.
I doubt you can get away with that. Yeah.
I've got to go. Thank you.
Yeah. Enjoy.
All right.
Yes.
Have a good day, everyone.
Have a good
Yeah,
day.
you too.
Yeah.
See you. Bye.
Yeah.
Yeah.
Bye-bye.
Oh, are we meeting at today or tomorrow?
I said today. Tomorrow to anyway, there is a class, so I'll be available for sure.
Okay.
But
so
today too is also
right?
good.
Okay.
Yeah.
All right. thank you.
2 o'clock or a little later after 2. Okay. So because others also wanted help, so I'm not sure whether you guys are all having it together or not. So it's going to be, let's say, if you have to wait for 10 minutes or so. Okay.
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 All right. Thank
Sounds
you.
good. Mhm.
Bye.